Right, welcome to VMware Explore. My name is Suhasini Raj. I'm the systems engineer for SD-WAN and SASE at VMware. With me today is Mike Pfeiffer. He is on the technical marketing team here at VMware as well for SD-WAN and SASE team. Thank you for choosing our session, the bits and bytes of VMware SD-Access. So please go through the small disclaimer before we get started with our session. All right. So this is a 90-minute technical tutorial. We have a lot of topics to cover. So I will go over the solution architecture, the components for the first 20 minutes or so, and then Mike will cover the technical deep dive of the solution, and then we also have the demo at the end, followed by time for Q&A as well. Any questions before we get started? All right, I'll take that as a no. All right, so we are all familiar with the traditional remote access VPN, where we have a centralized VPN concentrator, right? Usually that is located somewhere in the enterprise data center, and users that are located anywhere that needs access to these applications or even the workloads that are deployed on the public cloud will need to VPN into the data center and then gain access to these applications. The problem with that is it actually creates suboptimal performance because we are actually sending all the data to the VPN concentrator at the data center, which creates a bottleneck, right? So that hairpinning will lead to poor user experience, and also sometimes the users will have end posture security is compromised, right? So what is the solution for that? That is our VMware SD-Access. So this is a very simple and secure remote access solution that provides access to the users that wants to access these corporate applications or resources on the public clouds, no matter where they are. The solution is based on the principles of remote distributed network connectivity, as well as zero trust network access, so the users will be able to access these applications without having to backhaul their traffic to the data center. There are 4 different components. Basically, the first one is called the SD-Access client. This is a soft client, an agent that can be installed on end-user devices such as laptops or cell phones. This can also be installed on headless devices such as gas pumps, or it could be your ATM machines, or even if you have Windows servers that are running at your data centers, or if you have a remote desktop server, or any of those sorts, which are non-person entities. So you will be able to install these applications right on those servers as well. The second component that we have here is the SD-Access connectors. So when we install the application on the user devices, we need to be able to connect to something on the other end, right? So that is where we have the SD-Access connectors. So these connectors kind of front-end these resources at the public clouds as well as the data centers, and they advertise the IPs and domains of these resources. So users will be able to access these resources. And the third component is the SD-Access orchestrator. So this is our cloud-based management portal, which is where the administrators or users can log into the portal and then configure policies, security policies, the routing policies, and will also be able to monitor the user traffic and the networks. Then finally, we have the SD-Access relays. So these are the optimization relays that are out there on the internet, and they actually facilitate the end-to-end connectivity between different devices on the SD-Access fabric. So one point to note that is the solution that we are presenting here today was previously called SD-WAN client. But we have then since rebranded this solution to SD-Access because it actually the name kind of reflects what the product actually does. So I wanted to put that point out there. So just to show you how these components are stitched together, see the SD-Access orchestrator. This is the management plane component of our solution, and this has complete API integration, so the configurations can either be done manually, or you can also use APIs to make all the required configurations for the users. The second component, this is our control plane component, and these are the optimization relays that we have, and these optimization relays facilitate end-to-end data communication, not only just the control plane connectivity, but it also provides the data plane connection if required. And then finally, the SD-Access clients. So these can be installed, like I mentioned, on the end user devices, such as laptops or desktops, and also directly on the servers if you have any services running on these servers. And then finally, the connectors, right? So these can be deployed at the data centers or even on your public clouds. So this is how the components are stitched together: the management plane, the control plane, as well as the data plane. A little bit deeper into what the orchestrator itself is, right? So this is a multi-tenant orchestrator. When I say multi-tenant, what I mean is that if you are a service provider or if you are a partner that is managing multiple end users or the end customers, you will have the MSP access when you log into the orchestrator, and you'll be able to manage all of these enterprise users. The communication between the clients and the orchestrator, as well as the connectors and the orchestrators, uses TLS 1.2 or 1.3. That is the management plane communication. And then you will be able to configure everything on the portal itself. So this is a screenshot of the UI when you first log in. We do have IDP integration if users want to be able to log in through the SSO, and all of the connections, all of the statistics can be monitored in here as well. Optimization relays, right? So these are basically the turn servers or the stun servers, and these are deployed at various locations all over the world. And like I mentioned earlier, it not only provides the control plane connectivity, it provides the data plane connectivity as well if required. What I mean to say is, like, for example, if in most cases the user devices or even the connectors could be behind a firewall or could be behind a NAT device. So in such cases, it's sometimes not possible to resolve the public IP addresses to facilitate that end-to-end data communication. So in such cases, we rely on the turn servers to relay the traffic from one end to the other end. So the turn servers uses TCP and UDP ports 80.443 and 3478. And you don't need any configuration on the turn servers as such. So what I mean to say configuration is all you need to maintain is the configuration for creating the SD-Access overlay network. This solution is end-to-end encrypted, meaning the data traffic is completely end-to-end encrypted between the endpoints, and the turn servers or the relay agents absolutely has no visibility into this data. These relay agents also help to identify the users, meaning if a user tries to communicate on the SD-Access fabric, it makes sure to verify the identity of the user before letting the user access the resources on the other end. The SD-Access client, this is a screenshot from the SD-Access client application on a laptop. So when we install the SD-Access application and log into that application, two ways. You can either use the local username or password to log into the application, or use IDP like Okta or Ping Identity or Azure AD, any of these IDPs to log in. So once you log in, you will be able to see the username here here, which is usually your email, and then you will get an IP address, which is the SD-Access overlay IP address that's assigned to your client device. So this is a very lightweight application that goes on your user devices, and absolutely there's no hardware required. And then once the client logs in, they will be able to access only those applications that they are supposed to be accessing, right? So we provide tailored application access based on zero trust network access. And the users will not be able to access anything outside of that private network. And also, this provides optimized performance, better performance compared to your traditional remote access networks, because we are not hairpinning the traffic to the data centers. When I say performance, so this really gives a better performance in terms of accessing these applications, right? So when a user tries to communicate on the SD-Access fabric, the users first need to reach out to the control plane to make sure the user is verified, the user identity is verified. Once the user identity is verified, what the control plane does is it provides credentials, or it provides information for both the endpoints to create a secure communication channel between the two users. So once they have that secure communication channel, we actually build 3 different tunnels from the endpoint to the other endpoint. Let's say, for example, I have a user here on the left with a client application installed that is trying to access some resources within the data center, which is actually forefronted with the client connectors, right? So these client connectors will be advertising the IP addresses or domains of these resources behind it. So we will be able to have 3 paths connected. One is the point-to-point direct tunnel between the client application and the connector. The second one is through the relays. So one is the UDP via the relay, and the other is the TCP connection via the relay. So once the client picks up the closest relay or the best performing relay, it keeps doing the performance measurements based on the throughput, latency, or loss every 1 hour. So if the client finds out there is a better relay that's available, then it will actually switch to the other better performing relays. Then for some reason, if a path fails, then we have the traffic steered to the other paths in a matter of seconds, because these tunnels are pre-built and we don't have to wait for the tunnels to be established again. So we talked about the management plane connectivities, which uses TLS 1.2 or 1.3 between the connectors and the orchestrator, as well as the clients and the orchestrator. And then the data plane communication uses DTLS 1.2. We do not use any pre-shared keys. Instead, we use 2048 RSAs for encryption. And the certificates that are generated, these are on demand. And these certificates will stay on the device and is not shared with the control plane. The identity and context-based access control, right? So with this solution, we can actually provide restrictions as to what user can access what resources. So we can provide different access based on different types of rules and different types of policies within the device, and I'll go over those policies in a bit. But you can actually control these based on zero trust network access. So, like I mentioned, this is also single sign-on is enabled if you integrate with ITP, and any headless devices which can't authenticate themselves using the username or password, so can be authenticated with a one-time security token. The solution creates the entire network as a private network overlay, meaning it makes sure that all of your devices will be part of kind of a same private LAN. So I will show you what that means when we log in, when we go to the demos. Finally, so with the UI, you will be able to create all of your different policies, have complete end-to-end visibility for all of the different networks that you have created. This slide shows some of the locations we have our optimization relays deployed, and we will be adding more optimization relays as we go as well. I quickly want to talk about some of the different connectivity components that we have within the solution, right? So nodes basically these are the building blocks of our solution. So we define 3 different types of nodes: the user nodes, machine nodes, and the connector nodes. The user nodes are the ones where you install the application directly on the end user devices, your tablets, your smartphones, or your laptops, and they will be able to authenticate with a username and password. And as well as if you integrate with IDP, you can also log in with SSO. Some of the supported operating systems are Windows, Mac OS, Android, iOS, and Linux. So when a user logs into the client application, the SD-Access will provide an overlay IP address, and that IP address assignment is based on the device ID as well as the user ID. And once the user logs in to the application and tries to communicate with other devices on the network, the user will be able to add routes to its routing table for different endpoints as well. And all that can be configured, all the policies in the routing can be configured on the UI. The second type of node is the machine nodes. So these are the non-person entities, meaning they do not have a user associated with it, and they will not be able to log in with the username and password. They need to be able to be authenticated using security tokens, and we only support Windows end users for these types of nodes. So when the machine nodes log into the IP, and when log into the application, they will also be assigned an IP address on the overlay, and that's based on the device ID and the security token. And these machine nodes, once they log in, they will be able to advertise the host names or the internal FQDN of the services that they are actually configured to advertise. Then finally, the connector nodes. So these are a special type of NPEs, you may call it as. So these you can consider it as similar to a VPN concentrator at the data center, but this will be specifically for different types of resources. Like, for example, if you have one VPC created on your public cloud that has different workloads, then you can front end all those workloads within that VPC with one connector. So this connector can advertise all of the domains and IP addresses of the resources within that. And this again uses tokens for authentication, and the connectors can be installed directly on the physical servers, or it could be the VMs. So the connectors can also advertise, can be used to advertise the DNS, also advertise the DNS as well, and it will advertise the IP addresses, the domains, as well as the subdomains as well of the resources behind it. So SD-Access connections, right? So once we have the nodes, we will have to create different connections. We will have to create the networks for these endpoints to talk to each other. So we do have 2 types of topologies. So when we define the network, we can either define it as the hub and spoke, or you can define it as a mesh network. And depending on what type of network you define, you will be able to specify the source nodes, the destination nodes, and you also can configure different rules and context per network. The rules and context are different types of restrictions that you can apply for every user to be able to access the resources on a network basis. So with the rules, these can be used to configure layer 4 to layer 7 network services. So within the orchestrator, we do provide some predefined custom services and predefined services, and if you want to also create your own custom services, then you will be able to define it based on the TCP and UDP port numbers. Contexts are, again, these are the restrictions that you can apply as well, but in a more granular fashion, right? So if you want to make sure your users that are located in a certain location only needs access to these resources, you can configure that as well. So also you can specify my users need to access these resources only during a certain time, and only the Windows users will be able to access these services running on these servers, or things like that. So this will allow you to define much more granular roles, so you can provide access to the users as well as make sure you provide that end-to-end security. So two different types of topologies, like I mentioned. One is the hub and spoke. So this hub and spoke topology, when you configure, you can specify the sources as well as the destination. So the traffic here is unidirectional, meaning only spokes can initiate the traffic to the hubs. The hubs will be the responders only. And when you do that, the spokes can't talk to each other. It's just spokes to hubs. So some of the examples for this type of traffic would be your web requests or remote desktop requests or file download requests and all that. Then finally, we have the full mesh connectivity. So there are a lot of scenarios where you need communication between all of the devices or all of the users. For example, you want all of your users within your enterprise to be able to communicate with each other. So that is when you create server-to-server connection or the full mesh connection, right? So the traffic in this network is bidirectional, and any node can initiate traffic to any other node in the network. So that's why when we define this type of topology, we only configure the source nodes. So we don't specify the destination nodes in this. So for example, collaboration traffic or file sharing between different users in the network, things like that. So that brings to the end of my presentation session here. So I'll hand it over to Mike.
All right, we get to double click in all the things that Sue talked about. So let's dig into how we establish tunnels. So the first thing I want to hit you with is some terminology here. For traditional network engineers like myself, this is relatively new, stun and turn. These are WebRTC services, so for our collaboration engineers that are here, you're going to be familiar with this. Now, what I want you to take away from this slide is the combination of NATs that are out there. So we could spend an hour talking about stun, we could spend an hour talking about turn, so on and so forth. The key thing to look here is what we're trying to accomplish is getting two endpoints to communicate to each other over the public internet, right? We have exhausted public IPv4 space. Not everybody gets their own individual IP. That vision never came to fruition. So we have NAT. We have full cone NAT, address restricted, port restricted, and symmetric. So if we look at the rows, we look at the columns, imagine that's an A side and a B side to the equation. So everything that's in green that says point to point basically will establish all three connections that Sue just talked about. You've got turn via UDP, turn via TCP, and you have your direct communication, your peer-to-peer communication using UDP ports. So the big issue here is with symmetric. So symmetric NAT, if you're on the Wi-Fi now and you were to look this up, good chance you're on symmetric. If you are on your Android, your iOS, and you're connected to your carrier, good chance it's symmetric. So what ends up happening in this situation is we kind of lose track of what the external IP import is because that changes on us. So we're completely reliant upon turn. What I want you to take away from this is we can still establish a data path, no matter what the NAT combination is. You just may happen to lose one of those tunnels. So my recommendation on this is you deploy our SD-Access connectors, whether that's in AWS, Azure, GCP, Oracle, vSphere, data center, so on and so forth. Try to go for a full cone NAT type. That way you can have all of the tunnel options available. So if we go a little bit deeper on this one, this is what's going to happen. So this is a bit of an anachronism. I should have put the login slide first, because first we have to log into the fabric for this to happen, but I think this is still appropriate to some degree to put here, because for that client to figure out its public IP address as it communicates where it's at to other endpoints on the fabric it needs to communicate with, it needs to reach out to one of our relays and perform stun. So stun's gonna figure out what the public IP address is, what external port it used to communicate. It's gonna do an XOR mapping with its own information and return that back to the client. At that point, the client knows its NAT type, it knows its public IP address, so it can distribute this information to any endpoint that it needs to communicate with. The other thing that we're gonna do here is we're also gonna establish a turn session. So turn is kind of being used to facilitate communication. Those optimization relays, like what Sue was saying about end-to-end encryption, does not decrypt the traffic. They're just used as a relay to help facilitate communication should we not have an available direct path. And so we go ahead and preemptively establish a session. That way, should we need to do some facilitation like at the bottom right there, between a symmetric and a restricted, we have that available. So then that brings us to identity. So identity is a very key element of the solution. We want to know what the source is, we want to know what the destination is, and that's that zero trust principle that we're talking about. So when you initially use this, really good for POC testing, local testing, if you have a small user base, we can manage the accounts themselves, themselves for the users. So as you add user accounts, we'll send out a welcome email. Those users can set their password, and that's how they're going to do identity. Now, for larger networks that have access to an identity provider, like Sue mentioned, we can integrate our orchestrator using SAML 2.0 to bring in the identity information. So that's inclusive of user identity, group identity, and if you have SCIM, S-C-I-M, enabled, you can go ahead and port the user and group mappings directly into the orchestrator. You don't have to manually configure that. So when they get a login, they'll be redirected to the identity provider for authentication. If you have MFA enabled and all that good stuff, you'll be able to identify that user using the IDP. And then lastly, the machines. So this is applicable to the server nodes, to the connectors, to the headless devices. So anything that's not gonna have a user identity and be permanently logged in, we generate a unique security token that's gonna be used to authenticate that device to the fabric. So if we look at this from a kind of a flow perspective, so the first element is identity. So John at the top at example.com, first they're gonna enter their username into the client app. And so in this scenario, we're talking about SAML, right? We're talking about IDP. The backend is gonna say, hey, this user needs to be redirected to the IDP for login. So when they get redirected, the user is gonna have to punch in their credentials. Like I said, if MFA is included, then whatever that second factor of authentication is, and the IDP does the authentication for us, right? So once the authentication is completed, we get a session token for that user, and that information is passed to the backend, it's passed to the client. And so the client can then pass that to the backend and authenticate itself. So assuming this all works, the backend authorizes the login, it's going to assign the client IP address for use of communication across the overlay. And then at that point, the client itself will create the tunnel interface with all the information it needs to start forwarding traffic across the fabric. For a machine or a connector, it's a little bit simpler. You're gonna present that login token that you generated in the orchestrator UI for your authentication mechanism, and assuming that matches, then it too gets a client IP address, and it too creates a tunnel interface. But even at this point, no traffic's going across the fabric. All we've established is identity. So how do we figure out what should go on the tunnel? Well, there's actually quite a bit here. So when we create that tunnel interface, we're gonna do two things. Well, actually, probably like three things or more. There's a lot of things we're gonna do, so we'll go through each one of these. So of course it gets its IP address for IP communication. We also, interestingly enough, set its own IP address as a DNS server. And I'll explain why why we're doing that as we go on. Then we're also going to do the host routing table. So your connectors are going to have IP ranges, and these are going to be the private networks that you're trying to broker connectivity to, right? It's where your servers live, your applications live. So if you've advertised any routes, those are going to be downloaded to the host routing table on the operating system, and they're going to be pointed to the tunnel interface. Now, what we've done here is we've also manipulated the interface preference. So this is a Windows example. And for Windows, interface preference dictates who sees the DNS request first. Because if you have multiple interfaces, it's going to try and resolve. So because we're the preferred interface, we get a first crack at every single DNS request that comes in. So now our interception's working. So if we look at the DNS via tunnel, the bottom left there, this is an example of doing an NS lookup for compute to Acme internal, specifically to the own host IP address. So we get that DNS request, we know which connector is advertising for it, we send it to it, resolves it, and boom, we get the IP back. So now we know how to forward correctly on the tunnel interface. And assuming you've got the network in place to allow the communication to flow to that destination, then we'll establish the tunnels. So what does this look like from a double-click perspective? So just kind of resuming our journey here. The back end is going to send all the routes and DNS info to the client after login, and so that's how we know how to get the traffic on the tunnel. So when I try to initiate communication from john@example.com to that machine on the right, we need to first query the back end. Is this even permissible? So when you look at networks in our solution, they're more than networks, they're access control lists. Who are you? What are you trying to talk to? What protocol are you trying to communicate on? What geography are you coming on? And if that's permitted, then we're going to facilitate the communication between those endpoints. If it's not permitted, then you're denied access. So, and step 5, assuming we found a match, then the client's going to be instructed to generate those SSL certificates and initiate communication to the peer that it's trying to communicate to. And part of that is going to be generating a public key and making a fingerprint of that and exchanging it to the peer. And this is for mutual TLS authentication. This is why you can't intercept our traffic with an SSL decryption device. It can't really be broken or man in the middle because of this. So once we get that information over to the peer does the same exact thing, sends its public key information over, and then we start to initiate those DTLS communications. And assuming everything checks out, now we have tunnel establishment, now we can start forwarding traffic. So that brings us to DNS a little bit more in detail. So DNS is really interesting in the solution. We're not necessarily trying to connect you directly to your private DNS server in your internal infrastructure. We're taking care of DNS as a service for you. So the first way that we do that is with the machine FQDN mapping. So when you create a server or a headless device, and let's say it has an internal FQDN that your organization knows that your users are used to connecting to, you can punch that into the box that's over there that says FQDN. And so whenever they're on the SD-Access client overlay, they can still continue to use the FQDN they know, completely transparent to them, even though the underlying IP address of where that application resides is going to change. So if we look at this in a little more detail, we start at the top. And the top is, I'm at the corporate headquarters, I'm at the campus network. So when you drop into work, you're going to connect to the Wi-Fi, maybe you plug in, but there's a DHCP server out there that's going to hand you, what your DNS server is. And so once you get your on-premises IP, in this example 1076.0.20, and you query for that payroll app to the 10.0.0.53 DNS server on your network, you're going to be informed of where that host is, and your campus infrastructure is going to get you to that application. Whether it's directly there or you got to go through an SD-WAN appliance, your routing's already been plumbed and taken care of for you. Now, when you close your laptop, you leave for the day, you're back home, you fire it back up, you're going to get, you're not going to be on the corporate network. So what's going to happen is you're more likely going to get, a public DNS server, whether it's Google DNS or your carrier, whatever they hand you from an ISP perspective. You're going to be on a totally different network. So that routing infrastructure isn't there, but when you fire up the SD-Access client, the orchestrator has that mapping information you plugged in there, and it's going to go ahead and put that DNS information onto your client for you. So you're still going to use the same FQDN but this time you're going to get an overlay IP address, that 10.255 network in this example, and that's how you're going to communicate to this. So this is how we do a little bit of transparent communication with the DNS functionality in this product. But, the machines, that's one way to use this. I think a lot of customers of ours have been gravitating towards the connector, because the connector functions as an aggregation point for multiple users. And it can connect to multiple services behind it. So in this case, when you deploy a connector, remember this is a software-defined solution. So the connector is going to live on a Linux VM. That's going to be Ubuntu, CentOS, Fedora, and Debian, I think is what we have today. And what you basically do is you put this in your data center, deploy it on vSphere. And so you're going to have that private IP connectivity, but that host operating system needs to be pointed to the DNS server internal into your infrastructure, because it's going to be brokering the DNS on behalf of the clients. So assuming your host OS can do the resolution here, then you're going to be good to go. So as you specify your target domains, you can put in FQDNs, you can put in subdomains with wildcard. And so as those DNS requests come through on the tunnel, we'll be able to redirect them to this connector. Connector completes the resolution, and then the actual A record gets sent back to the client. So if we look at this from a stepwise procedure, left to right, going up the stack, client sends DNS query, connector gets it, forwards it to the DNS server, DNS server resolves it and gives it back to the connector, and then the connector gives it back to the client. So at this point, you have the actual IP address of what you're trying to get to. And you may not necessarily have connectivity here, right? Because there's still an IP element of this. You've got DNS taken care of, but now we need IP connectivity. So there's a couple of options on that. So if we were to still continue to use target domains here, there's a checkbox to the right called tunnel. And so this adds one more wrinkle to the equation. That host Linux OS needs to be able to route to the destination, which I'm assuming if it can reach your internal DNS server, likely it can also reach that internal resource. So if you select the target domains, we do something really kind of interesting here. Or sorry, you select tunnel beside target domains, we do something really interesting here. We have a second IP range that you identify when you first onboard the solution. And it gives us the ability to play around with the A records and to manipulate the IP traffic to come to the tunnel without you having to advertise any IP routes. And I'll detail that out in the next slide. If you weren't using this, then you'd have to use the IP range methodology to be able to get the IP traffic to the correct destination. So this is the same exact as before, but we go all the way to the right where we got those boxes and arrows pointing down. So when the client gets back the actual A record, before it even informs the host operating system, it's going to do a swap. We're going to take an IP address out of that secondary range that I was talking about and give that back to the host OS. So in some examples, you may see like 10.254.0.0.0, or that might be too many zeros, but 10.254.0.0 for that payroll app.acme.internal. Even though it may really be, known to your organization at 1076 or 10255. So we're basically tricking it. So when the host OS forwards, it says, well, I need to take this to the tunnel because that's where this route goes. And then before we forward it on to the actual connector, then we swap the IP destination packet to the correct IP address so it gets to the correct destination. And so this kind of helps with seamless integration into your environment. So, moving right along, And I know this is a lot to take in. We'll have time for Q&A at the end. And afterwards, Suhasini and I will hang out in the hallway to take questions. So plenty of opportunities to double click on some of the things we're talking about. So how to design networks. So how many of you have actually been in this product? Just a couple? Okay. So it's a good thing Sue did the tee up. So this was, my intention here was to go really deep on this particular topic. This information is still going to be useful. Hopefully it gets planted in the back of your brain. As soon as you get to use this, it's all going to click and come together. So when you first get the solution, what I've seen a lot of people do is it's so easy to get things connected. They create a single network, they lump all the sources together, all the destinations together, they fire it up, and they have connectivity. So if you were to do this in this situation, you've got corporate, you've got HR, you've got IT, you've got point of sale, connected all to the data center through a single connector. So that's good for a connectivity, for just general connectivity, right? This is minimal configuration. You can get things quickly up and running for basic testing. So you can essentially have a, for lack of a better term, a VPN-like connectivity within, minutes, if not quicker than that. But the con is everyone has access to the same exact thing, right? And in the world that we're in today, we want isolation between traffic. We want groups to be segmented out so they're not, over-provisioned access. We're not creating a situation where, your organization can be breached. So, and single connector may not scale to meet demand, and it also may be a single point of failure. So what we're gonna do is we're gonna start improving this design, and we're gonna create 4 networks. So when you're in this product, configuring things, what I want you to think about, and we'll see the progression here, is to some degree, more is better. Not to excess, but more networks is better. So we're gonna go ahead and divide this up into 4 networks. So all we really did here, though, is we've articulated the same type of connectivity with just 4 different network statements. So we haven't really moved the needle, but we're preparing ourselves to move the needle. So we're prepared to refine access controls, but we still have all the same problems as before. So we're gonna do some refinement. We're gonna start adding rules to these networks. And so maybe the corporate team needs access to these servers or these applications that use TCP or UDP and these set of destination ports. And you do that for each of these network segments because maybe it's not all the same. So you go ahead and slap these on. So yeah, you've done some restrictions here, you've limited some of the connectivity, but because you're using that single connector, you're still allowing them to reach the same IP destinations, the same DNS destinations. So you could inadvertently expose a server on, say, like port 22, like SSH, that shouldn't necessarily be exposed to like HR. That's more of an IT function. We need SSH, HR doesn't. And we still have the single point of failure problem. So, but we're getting close. We're getting on the right track. We want to add some context to this. So maybe we want to put a time range to this. Maybe there's a set of operating systems, be it Linux, Mac, Android, Windows, so on and so forth, that these groups of users use, and we want to do that posture checking. Maybe we want to check to see if they have an antivirus installed, and there's no infections being reported. So now we're getting more restrictive on the access, but we still have kind of that exposure issue that I've been talking about. We still have that single point of failure from a connector, and we're still concerned about scale. So, this being a software-driven solution, deploy more connectors. Like I said, these are just Linux VMs, so easy to spin up in the cloud, easy to spin up on vSphere. They're pretty moderate in terms of the resources that they're going to consume. 2 virtual CPUs, 4 gigs of memory, so not too heavy of a load there. And you can also do less. It just kind of depends on how much traffic and how many users or devices you're expecting to connect to them. So now we created 5 connectors, and I added a 5th service here called shared services. So maybe there's common services that corporate HR and IT need to access, and it doesn't make sense to kind of like, I don't know, just like lump it all together. So you want to break it out so you can kind of be more precise, more articulate in your policy. So when we do something like this, we expand out what our networks are going to look like. They have dedicated connectors. They are scoped for what those users should be accessing. We have it tailored to the protocols and services that they're supposed to be connecting across. And now we have this really refined network to where we're going to know who the user is. We know exactly what applications they're supposed to access and how they're supposed to get there. And we have this very much locked down to the minimal access set that they need to be able to perform their job. And one thing here, highlighted in the red box, is you can see where I just kind of threw the shared connectors in there. And that's kind of getting us back to the same problem that we just solved, right? I may have accidentally over-provisioned access to shared services. And so the really cool thing about the solution is just create another network, because it literally takes seconds. So create a fifth network, carve that off into shared services, and then when you add it, you can scope it for what it needs to be scoped for. And at this point, we've taken a single monolithic connector, and you can draw that comparison to like a single monolithic VPN concentrator. We broke it up into its constituent components. So now we have 5 connectors. We have distribution of what that is so we can scale. We don't have a single point of failure. And now we've kind of dealt with also like our access control restrictions that we'd like to enforce on the network. So now we're going to double click into the connectors themselves. So there's a couple ways that you can deploy these connectors. You can do them in a NAT mode, you can do them in a routed mode. So the NAT mode is the default and perhaps the easiest way to deploy one of these connectors. You throw them into your existing infrastructure that you probably already have plumbed. So if it gets an IP address in that infrastructure, all the overlay IP addresses get natted to that IP address, and then it just routes into your existing network, right? No issues there. The cons to this, though, is it can hide the client source IP. So if you want to expose the client IP address, you're going to have to go with the routed mode. Otherwise, you would only ever see the IP address of the connector as it routes into your data center or the cloud. And then, of course, because we're doing source network address translation, we're limited to about 64,000 simultaneous translations at a given time. So that's just a function of SNAT. So if you needed to break out of that or do something a little bit different, you can do routed, which stops the natting, so we don't have to worry about hiding the source IP. We don't have to worry about the limitations of translations, but you're going to have to do some modifications to your infrastructure. You're going to have to know how to route that traffic back to the connector, wherever it's coming from. And then it could also require some modifications on the connector's host operating system itself. And then, because the connector is a Linux VM, you can throw as many interfaces as you want on this. So the most common deployment is a single interface, so kind of like a simple kind of deployment where both the tunnel traffic and then also the traffic into your local area network will just come in and out of one interface. So you have it set up, it just relies on its default gateway. So it's a really kind of simplistic deployment style that may fit well in your environment, may not. One of the reasons for that is, like me coming from an enterprise background, we were very big on security zones, and interfaces kind of dictated where traffic should be going. So, whenever we did our VPN solutions, you had a clear delineation between the WAN and the LAN, and those went to, their respective security zones on the NGFW. So that's where you can bring multiple interfaces into the mix. So you bring in multiple interfaces. Really, all you have to do at that point is make sure your routing on the host OS is set up correctly. And then, of course, what it's connecting to in your surrounding infrastructure is set up correctly for traffic to route back. So if we look at this from a deployment perspective, this is the first option here, first flavor, single interface design with NAT. So like I said, all traffic on the left, the overlay network, those employees A, B, C, they're going to get NATed to that Ethernet 0 10.1.10.20 network. And then assuming it's all set up in your infrastructure and the routing infrastructure knows how to get back to that /24 subnet, and it knows how to forward to the target application, it's all done. And so a lot of times when customers do this, it's pretty quick to be able to start connecting users to applications. So if we turn off routing, basically what we need to do is advertise the IP route of the overlay network into the rest of the infrastructure. So this can be done doing a simple static route, because we don't do dynamic routing today. So in your upstream router, you would do a static route and redistribute that into your routing protocol. For everyone that's screaming at me, like, where's the ACL, where's the route map? Definitely make sure you control your redistribution. You can't hold me accountable if you don't. But yeah, that's just kind of a simple example. Now, one thing that I did not depict here that I should have is on the Linux VM itself. So hopefully you've got some familiarity with Linux. If not, we've got it in the product documentation. You have to enable IPv4 forwarding. So when we do the NAT mode, we do that for you by default. But when you disable NAT, which I'll show you in a further slide, you have to turn on the forwarding of IP traffic on the host Linux operating system. And so moving right along, when we introduce multiple interfaces with NAT, the only wrinkle here is now we're looking back at the Linux operating system, the host VM itself, and we're making sure that routing table is correct. Does the default route to the internet point out the interface that's intended for the internet? The LAN traffic, the 10/8 network, if you will, is that pointed out the right interface to go to the resources hosted in your environment? So that's all you have to do with that. And then, of course, with the routed environment, it's more or less the same as I talked about previously. A combination of two slides, right? So the routing infrastructure needs to know how to get back to it. And then, of course, the host Linux OS needs to know how to make that left-right decision in terms of internet or private LAN traffic. And so this slide is kind of like the art of the possible. And what this is illustrating here is connector-to-connector communication. So if you wanted to bridge two separate network domains that are across the internet, this is one method that you could do this. So pretend you have Azure, pretend you have AWS, and you need those two networks to communicate to each other. You could deploy a connector in each one of them, and then as long as you point the IP ranges that they're responsible for advertising, you turn off NAT functionality, and you enable IPv4 forwarding on the host Linux OSs, and of course you advertise the routes in Azure and AWS respectively to those ENIs, then you're going to be able to then start bridging these network domains using the connectors. So kind of a lot to take in there. If you're like me, I started out networking on the traditional router equipment, but then slowly progressed into Linux. At first, it was kind of seemed like a lot, but once you get into it, it really makes a lot of sense. And in the upcoming slides, when we talk about automation, that's kind of the key to unlocking the power of the solution. So let's dive into the API. What I really want to talk about is the art of the possible here. So there is an API here. You can generate a token for this. And when you generate the token, you can use it to create and manage contexts, connectors, groups, rules, machines, users, and networks. So sorry about that. So everything that you can manually connect or manually create in the GUI, you can also do via the API using this authentication token here. If the authentication token is ever lost or compromised, you can just regenerate a new one. It'll invalidate the previous one. So you can interact with the API using any tool that you're comfortable with: curl, Postman, Python, software development kit, or other languages that you may use in your organization. So on the VMware Code Exchange, there is sample code, an SDK here that you can use for interacting, and that's what the CLI is showing in the example here. So you can make your REST calls, you can query network IDs, you can create what used to be called V2 LAN IDs. So one thing we didn't touch on is this technology came to us from Ananda Networks. And so Ananda Networks, they originally called this a V2 LAN. So their idea was basically a virtual layer 2 LAN that was kind of ubiquitous across the fabric. So you'll see some of the older nomenclature here, but that's still referencing a network. And so once you start interacting with the API, think about the other tooling that you can use in your environment to really unlock the potential here. So Ansible comes to mind, right? Ansible is perfect for managing Linux host operating systems. So here is a sample of an inventory that I use. So Suhasini will be going through a demo, and she built her demo lab using this functionality here. So one thing I will say is there are tokens in here. If you're going to use this in a production capacity, store your tokens securely. You wouldn't store them on a file locally on a machine like this, but for a lab, it's pretty simplistic. So at this point, we know how to connect to these endpoints, and we know how to execute the Linux commands on them to get the manipulation we want. So we can deploy these things consistently, in mass, and at scale. And so here's an example of a playbook where we're just doing several things. And this is around the connector and also the machines. We're installing the correct repository to get the software. We're running the update on the package manager. We install the service, we upgrade it to make sure it's up to date, and then we can pass that token and log in. So you could technically deploy like 1,000 of these things. So it's really good for doing testing or just kind of, keeping track of how you're going to provision these environments, especially for, if you're managing a lot of customers, this may be an effective way to do this at scale. And I bring Terraform into the equation, so we don't have a Terraform provider for this yet. But the reason I bring Terraform into the equation is because think multi-cloud. Terraform's that really good, just like general purpose language, where you can build on vSphere, you can build GCP, Azure, AWS, so on and so forth. And so if this is all predicated on Linux VMs, EC2 instances, compute instances, use Terraform or something like that to be able to deploy your lab, to be able to deploy for customers, because as you start getting into infrastructure as code, you can start maintaining a single source of truth, and you can quickly recover from any failure situations that may encounter in those environments. So why did I bring these technologies up? Well, you can do some pretty interesting things with Python. So you can kind of think Python is kind of the orchestration element to all this, because we're using disparate tools here. So Python can be used to trigger the Terraform that builds the infrastructure. The API, the SD-Access client API, can be used to build the networks, the contexts, the nodes, get your one-time passwords that you're going to use to authenticate these devices to the fabric. Then Ansible is going to go out and install all the software and log in all the devices. And Python is the one that's pulling all the levers to making sure that this all happens. So as you'll see that lab that's coming up here in the demonstration, this was all built using this methodology. So I just wanted to give you a look into the art of the possible. And with that, Sue?
All right, so for the demonstration, we have a very simple topology here. So if you look at the left-hand side, we have two different set of users that we have grouped into app users and server users. And on the right-hand side, we have SDA Connector 1 and SDA Connector 2. These are the connectors that we have deployed on the public clouds. And there are certain resources behind this, so the users will be able to access these. And the data center portion of it, we have the client apps directly installed on the servers, and we have web servers running on these, so the users on the left-hand side, which are part of the server users group, will be able to access this. So the whole intention is the app users here will be only able to access the resources behind the connectors in the public cloud, and the server users will be able to access only the resources within the data center where these servers are hosting the SD-Access client application, right? So all of these configuration, if you look at the SD-Access overlay network here, will be done as part of our orchestrator. All the rules, all the policies, the context, everything will be within our orchestrator. So real quick, I'll jump into the orchestrator. It's not switching, do you think?
You got it?
I have it set. It's not switching.
Oh, there it goes.
Okay. All right. This is how the orchestrator looks when you log in. The first page that you land is the dashboard page. This kind of gives you an overview of the user and the network activity and different types of networks that we have configured within the orchestrator. Right, so at the top you see active users and active servers. What this means is that this gives a total number of users and total number of servers that are configured as part of this SD-WAN fabric. So we see here there are 4 total users versus the 5 active users. What that means is that we had 5 users that were configured in the past 7 days, and we have removed 1 user. So it will have that data for the past 7 days. Then we have 2 active users as well. Then the network clusters here shows how many networks we have configured. And here, if you hover on these circles, this basically shows you how much data and where exactly this data is being transmitted on the SD-Access fabric. And then below here shows the most active networks. So these are the networks that we have configured. If you remember from my presentation earlier, so I had the hub and spoke topology and the mesh topology. So these are the networks that I've created in my portal here. And then it also gives you the list of active users that are accessing the fabric. And then to the right, you see 3 different sections: the data, the connections, and the unique users. So all of this data that you see here, the data is stored for a period of 7 days. Right? So the data gives you how much data has been transmitted over this SD-Access fabric in the past 7 days, and then how many connections have been made in this over this SD-Access fabric, and then how many users are there in total that are accessing this network at the moment. So quickly, I would just want to run into the nodes section. So if you remember the nodes I talked about, there are 3 different types of nodes: the user nodes, the server nodes, or the machine nodes we call it as, and then the connector nodes. So here under the user nodes, I have configured 4 different users. And if you look at these users right now, none of the users are logged in at the moment. So when we log into the client app, you will see a green check mark, and I'll show that when I log in back again. So what you see here is the users, and then when the users have logged into the SD-Access client application, application, they will be assigned an IP address on the overlay network. So that's the IP address that you see. This is a unique IP address per overlay network. And it also shows what type of user device, what operating system the user is running, and then the version of the client application that's running. And if you expand here, so you will also be able to see what different groups these users are part of. So just for the demo purposes here, so I have created user Suhasini and user Grace Chang and added them to both the groups, the app users group as well as the server users group. So these two users will be able to access the resources both on the public cloud as well as the resources in the data center. Moving on to the server nodes. So I've created two different servers in my demonstration here. And so these servers will also have the IP address on the overlay assigned to them as well. And I've put these servers as part of a server user mesh. So I will talk about the connection in a little bit. Then moving on to the connectors itself. So I have two different connectors. So these two connectors are giving access to the resources that are on the public cloud. So just to look at the configuration of the connectors right here. So I have the interface name here for the connectors. So if you remember from what Mike mentioned in his presentation earlier, you will have to specify the interface for the connector. And then you can also specify either the target domains or either the target IP address ranges. It could be these IP ranges or the IP address itself. So the connector can advertise these to the users. Going on to the connections section. So this is where you will be able to different types of networks. You can configure either the hub and spoke topology or the mesh topology. So for my first type of network here, users to cloud, I have it configured as hub and spoke, which means the users that are part of my app users group will be only able to access the applications on the public cloud behind the connectors. And because this is configured as hub and spoke, my app users will not be able to talk to each other, right? They can only access the resources behind the connectors. So I have specified my source nodes, which is my app users. So, and then the destination nodes is my connectors. So I've actually put these users and connectors as part of the groups. So it's easy for us to include these in the destinations here, right? So, and you can also specify different rules and contexts for each type of user or each type of user groups. The second network that I have here is the server mesh. This is the mesh topology that I have, and I'm allowing all the users and all the servers to be able to communicate with each other. So in this configuration, we only have to specify the source nodes. So we don't have to specify the destination because anybody can initiate communication with anybody in this type of network. And then again, so same, if you want to define any kind of rules or contexts, that can be defined as well. So real quick, I have rules configured here. So here I'm allowing all the network services. So when you pick one network service, so there is an implicit deny at the end. So make sure you specify all the services or all the rules that you want to be allowed on the network. Right, so if you want to create any custom rules, you can create based on the TCP and UDP port numbers as well. Then for the context, so we have this rule, this context created where we are allowing all OS types to be able to access the network. So for the context, you can specify location. So if you look at the drop-down here, you can pick any region that you want the users to be able to access from. But again, everything has the implicit deny at the end. So if you pick one specific location, only users from that location will be able to access the resources. So again, you can specify the time range, different operating system, and also specify the device posture, right? So device posture is, like Mike talked about, you can specify antivirus. So if there is certain antivirus running on the device only, then that user will be able to access the network and things like that, right? So now that we talked about different users and different connections, I quickly want to jump into the user device itself and show how it works. So if you can see this one, so I have user Mike. So let me log into the client application with this username. And because I've already configured, I've integrated IDP and configured all the IDP configuration, so user can use a single sign-on to log in. All right, so if you see the user was able to log in, and on the right top right, you see the username that the user has used to log into the client application, and then the user has been assigned a unique IP address on the overlay network. If you click on this icon below, it gives you different options here, and if you click on the network connections, you'll be able to see different resources that the user has access to. So this user, if you remember from my topology slide, this is part of the app user. This user is part of the app users, and this user is allowed to access all the resources behind these two connectors. So this user can talk to two different connectors and access all the resources behind the connectors. Right, so now if I open my browser right here, sorry. So this is a web server that's running behind my connector, and Mike is able to access this web server. And I have another web server that's running in my data center on one of the servers. And because Mike is not part of the server users group, he is not allowed to access this service. So if you see, he is not able to log in. Now quickly when we go into the CLI, so there is CLI available here, and as soon as the user logs into the application, you will be able to log into the CLI and verify some of the commands as well. So the CLI is the SD-WAN client CLI, and if you type help, you will be able to access different commands. You'll be able to see different commands that's available here. And then version shows you what client application version you are running. And then the IP here shows you the IP address, the SD-Access overlay IP address that has been assigned to this specific user. And then if you look at the routes, so you will be able to see this particular user has routes to both the connectors, so A connector 1 and connector 2. And this is the connector's IP addresses, 10.255.0.33 and 0.32. So these are the overlay IP address for the connectors itself. Then if you look at the connections, so this shows 3 different tunnels. If you remember from my slide earlier, so I showed you the client building 3 different tunnels to the other endpoint. One is the direct point-to-point tunnel. The other 2 are the tunnels via the relays. Okay. Sorry about that. All right. So these are the 2 connections that this user has. The first one is on this network, right? So this is the network users to cloud apps, and then he has connection to the connector 1, and the other is the connection to the connector 2. So these are the public IP addresses of these connectors. And if you look at this right here. So our connection is a direct connection from the client to the connector, and that is because we have the lowest latency on this point-to-point link compared to the other two tunnels through the optimization relays. So traffic always uses the tunnels with the lowest latency, as you can see here. So quickly going back to my other user. So my other user is part of both the groups, the app users group as well as the server users group. And if I look at the network connections for the other user, she should be able to access all the applications. I think this was logged out. Let me just log out and log back in. All right, now this user is logged in. So we got the IP address as well on this fabric for user Grace. And now if we look at the network connections, Grace should be able to access all of these connectors as well as the servers at the data center. Right, so similarly, if you look at the routes and the connections, so everything should be available for Grace to access as well. And because Grace and Suhasini are part of both the server users group as well as the application users group, they are able to talk to each other. So you will be able to see the route for user Suhasini on this as well. Versus if you look at user Mike, he was not able to talk to any other users in the apps group because he was configured as a hub and spoke topology. And because this user is not logged into her client application, you see this user is not active. So going back onto the portal, if you look at the monitoring section, so you will be able to see the connections, the events, and all that, right? So if I filter based on the block connection, you'll be able to see that user Mike tried to access the web server in the servers group, and he was not allowed access because he was not part of the server users group. And then lastly, I want to talk about these settings. So just real quick, you can add in administrators in this section and also configure the IDPs if you want your users to use their SSO to log in. So here I have used Okta for my IDP, and if you are using SCIM, you can also configure SCIM like Mike mentioned. So SCIM actually helps to port your users and groups directly from your IDP. Then the endpoint posture. So this is an enterprise-wide setting, and if you configure this and add this to your context, this will actually restrict the users from accessing the resources if they're not running a specific antivirus on their devices. So if you choose any, so you can have any antivirus running on your device and you'll be able to access, but if you pick one of these specific antivirus, then you should have that specific antivirus to be able to access. So otherwise, we have the implicit deny at the end. If you don't have an antivirus running, you will not be allowed to access resources. And with that, we are end of the demo, and that's all I have for the demo. Anything, Mike, to close on? Okay. All right, so switching back to our presentation, the key takeaways is that for any new solution or any new product, the key idea is to just learn the fundamentals and learn how to deploy a certain solution and how to design the networks and use automation and APIs that Mike talked about to scale the networks, so which actually simplifies your deployment as well, right? So, anything that you want to add, Mike?
No, that covers it. So we're going to go ahead and move into Q&A. So if anyone has any questions, microphone at the center. If you could come up so everybody could hear the question, we'll try and get those answered for you.
Okay, so if I'm a VMware customer and I have deployed VMware SD-WAN solution, right? So let's say I have my overlay flow control routing table, right? And now if I deploy the SD-Access client overlay network, is there going to be an integration between those two overlays without having to deploy a new connector, or am I still forced to do some sort of integration between SD-WAN routing and the connector?
Yeah, so that's still accurate today. So they're two separate solutions, two separate control planes. So the interaction point between those two would be using traditional routing, right? Whether, like it's an edge or a gateway level or partner gateway level, you would have to configure the routes between the two. I don't want to speak to roadmap, just keeping the session focused on the current capabilities we can deliver. But as an existing SD-WAN customer, just reach out to your SE and we'll get a product manager to talk to you about what the future looks like.
Okay, and if at this point there are treated as two different customer solutions, and when I have access to the orchestrator, I'm not going to be able to see the management of both solutions in the same orchestrator. Still that different as well?
So stay tuned. Developments are coming. As it stands today, as separate portals, your orchestrator would be separate from this as it is today. But yeah, definitely stay tuned. We're definitely working on that.
Thank you.
Yeah.
Quick question. Do you have any governance over bandwidth utilization?
Do you want to take this one?
Oh, go ahead.
Sorry, so when you say bandwidth, could you repeat that?
Yeah, governance, meaning can I assign specific bandwidth for the client so they don't overwhelm the network or any situation like that?
So as it is today, no. What that's really going to be a factor of is, like, let's say you have one connector and one user, and they're actively using that tunnel. It's going to be able to consume all the resources that are available. If you have two users, then it gets divided by 2, and if you have 3 users, divided by 3. So that's kind of how it's working today, but there's no rate limiting in the product yet.
Thank you.
All right, anyone else? No? Cool. All right, well, with that, we're going to end 10 minutes early, so grab a water, grab a snack, stretch your legs before your next session. Thank you.